This will be the next in our series, Our Place in the Universe. And here we'll take a look at our sun and some important ideas we'll encounter. Now, we're familiar with our sun in pictures like this. Scenes of sunsets taken with a typical camera. Now, if you put a telephoto lens on and put a solar filter over the lens, you can get more close-up pictures of the sun. The sun is a star. And in this photograph, we see spots on the surface of the sun. Those are sunspots, regions of strong magnetic fields. But what are stars made of? Well, all material objects are made of the elements. So here's our periodic table of the elements. Now, which of these elements are stars composed of? Let's remind ourselves that the simplest element, hydrogen, consists of one proton in the nucleus of the atom and one electron. The next simplest would be helium, 2 protons, 2 electrons, followed by lithium with 3 protons, etc. Well, stars are made of mostly hydrogen and to a lesser extent helium and small quantities of some other elements. So stars are made of the simplest elements in the universe. So a star is a giant sphere of hydrogen gas held together by its own gravity. Gravity causes the hydrogen to condense, increasing the temperature and pressure high enough to cause nuclear fusion, which releases energy. The outward pressure of nuclear fusion prevents the star from collapsing due to gravity. In this diagram over here, then, we see the battle between these two forces of nature. Gravity tends to collapse, to condense the cloud of hydrogen gas. But as temperatures and pressures increase, a nuclear reaction occurs in the core of the star, nuclear fusion, and that generates energy, and that tends to expand the star. When these two forces are in balance, we have a stable star. So hydrogen is the initial fuel for the star, and during nuclear fusion, the element hydrogen is fused together to form the element helium. 4 hydrogen nuclei are fused to make one helium nucleus. Over here on the right, we see the details then. So the hydrogen nucleus is simply a proton, a positively charged proton, and it takes 4 of them smashed together to create one nucleus of one helium atom. Notice then, in this process, 2 of the protons are in a sense converted into neutrons. And there is a loss of mass in this process, and that mass is converted to energy by Einstein's equation E equals mc squared. That's the energy that is released during the fusion process. Now, why does the star need such high temperatures and pressures to start the fusion process? Well, that's because protons are positively charged. So here's a hydrogen nucleus right here. It's a positively charged particle. And as positively charged particles are brought next to other positively charged particles, there is a force called the electromagnetic force that makes the particles repel each other. So it's going to take incredible temperatures and pressures to force these two particles together. And that's why then fusion only begins at sufficient temperatures and pressures. You have to get the particles hot enough so they're moving fast enough that they can overcome the repulsive force and they can actually collide. And when they collide, then you get a release of energy, and that's the fusion process. So a star's core generates the energy equivalent of 1 billion hydrogen bombs per second. So what stars are doing in their cores is the same as what the hydrogen bomb does. It fuses hydrogen nuclei to form helium, and that releases energy. So stars shine because the nuclear furnace in the core makes the surface of the star hot, and hot things glow. So the surface of the star is more hydrogen gas here. But the idea is the nuclear fusion is generating lots of energy that is heating up the surface of the star, and hot things glow. On the left, we see a picture with lots of different stars of different color. We see blue stars and orange stars and red stars and white stars. On the right, we see that the difference in color is related to the surface temperature of the star. The red stars have the lowest surface temperature from 2,400 degrees to 3,700 degrees Kelvin. Yellow stars are 5,200 degrees to 6,000 degrees Kelvin, and the blue stars are the hottest, more than 30,000 degrees Kelvin. Now, this temperature difference on the surface is related to the mass of the star. We can see that the hottest stars are the most massive stars, and the idea is with more mass, gravity can compress that volume of gas and reach higher and higher temperatures in the core. So the core is hotter. With a hotter core, it heats up the surface of the star to a greater degree. Less massive stars, they perform nuclear fusion, but the core is not as hot. It doesn't heat up the surface of the star as much. And in a later lesson, we'll learn why it is that the hot surface emits more bluish light and the cooler surface emits more reddish light. Now, stars also emit high-energy particles called the solar wind. And these particles are dangerous to living things. Now, fortunately, the Earth's magnetic field shields us to a significant extent. Now, these high-energy particles are generated by magnetic phenomenon on the surface of the star. These high-energy particles are charged particles like protons and electrons, and when a charged particle enters a magnetic field, it feels a force. And so the magnetic field of the Earth can steer these particles away from the Earth. So living things on Earth are protected by the magnetic field of the Earth. Now, what happens when the star runs out of hydrogen? Well, this diagram shows the origin of stars and their possible fates. First on the left then, stars originate as a cloud of hydrogen gas. Gravity compresses that gas until nuclear fusion begins. But now there's a difference between what happens with a small star and a large star. The small star will end its existence as a white dwarf. Larger stars have a more cataclysmic ending, but we'll get to that in a moment. But for both kinds of stars, as hydrogen is used up, the fusion process continues with helium, and this creates even heavier elements, atoms like carbon. So, in general, all of these fusion processes create atomic nuclei with greater numbers of protons, or the heavier elements. Now, when hydrogen is used up, gravity compresses the star to reach temperatures where helium can fuse. So again, the initial fusion with hydrogen makes the heavier element helium. Helium is heavier because it has 2 protons. The hydrogen nucleus had only 1 proton. But when hydrogen runs out, the gravity now will compress the star even more because fusion has begun to slow down. The hydrogen has run out, and so gravity starts winning the battle. But as gravity compresses the star even more, the temperatures and pressures increase to the point where now helium nuclei can start to fuse together, again releasing energy. So when you fuse helium nuclei together, you make even heavier elements, like carbon atoms. In fact, the white dwarf itself is thought to be just a huge mass of carbon, pure carbon. Now, stars continue this chain reaction of fusing heavier and heavier elements, but stars cannot fuse iron to form heavier elements. So iron is the end state. When large stars run out of nuclear fuel, they explode in what is called a supernova. The heavier elements created within the star and those created during the explosion are now distributed back into space to be incorporated into newly forming stars and planets. So stars and their explosions are producing new and heavier elements. For example, this is a picture of the supernova remnant, so the remains of a supernova, Cassiopeia A. And that supernova explosion ejected 70,000 Earth masses of iron and 1 million Earth masses of oxygen. In other words, these stellar explosions are producing large quantities of the heavier elements. You'll recall the core of the Earth had a lot of iron. And oxygen, in fact, is the most abundant element on the Earth. Well, a supernova is producing 70,000 times as much iron as exists on the entire planet, or 1 million times as much oxygen as exists on our planet. That's a lot of material. We can think then of a cycle of star formation and then demise. Stars form from clouds of hydrogen gas. Gravity compresses them. They begin nuclear fusion, but they're going to run out of their fuel, and they may end their existence in giant explosions called supernova. But the nuclear fusion process and the supernova explosion itself creates heavy elements that then will mix back into space with the hydrogen gas that was still there. So imagine we can go round and around this cycle. We can have first generation stars explode and produce some heavy elements that mix back in with the remaining hydrogen gas, and then second generation stars and third generation stars, and in time we're going to be enriching interstellar space with heavy elements forged by stars. So in this depiction of the periodic table, the way they do the color coding here has to do with the way the elements were formed. You'll notice the Big Bang is the origin of our universe. So hydrogen and helium were the first two elements formed early after the origin of the universe. So we can say the universe itself produced large quantities of hydrogen, to a lesser extent helium. After that, it was stars that are producing all of these other elements. We have the green dying low mass stars, purple merging neutron stars, and the kind of the yellow-orange exploding massive stars, the gray exploding white dwarfs. So in other words, lots of the elements on the periodic table here were produced inside of stars or during stellar explosions called supernova. So when we tell the story of the universe, it's a story in which in the beginning there was just sort of hydrogen and helium, and then stars show up to make all of these other heavier elements, out of which future planets and living things will be made. So stars are element factories. Here we see a cartoon picture of a star, and here are all the different kinds of elements that differ in the number of protons in the nucleus of the atoms. And when stars go kaboom, they make even heavier elements. So stars are the factories that make all of the different kinds of elements that make up the material things in our universe. So stars produce the materials to make planets. And again, then we can say it this way: planets are star stuff. The elements that make up our Earth were formed inside stars or the explosions of stars. And we can go further. We'll start up here at the left. We have a star making heavy elements due to nuclear fusion in its core. The explosion can create even heavier elements, and these heavy elements are precisely the elements that will make up future planets. One of those planets, life emerged. So since life emerged on planet Earth, all living things on Earth are also made of star stuff. We, all of us living things, are star stuff. Now, previous generations of stars made the elements found on Earth. So our sun is busy making the kinds of elements that we find in our bodies. But that process is quite removed from us right now. It's happening inside our sun. For us here on Earth, what's really important is the energy that is emitted from the sun. Today, our sun provides energy that sustains organisms such as plants and other photosynthetic species, which are the foundation of most food chains. So in the history of life on Earth, some living things evolved the ability to harness sunlight energy, to use the sun's energy, capture that energy to power some interesting chemistry. Photosynthesis is complicated chemistry, but it can be boiled down to this simple process. Green plants can use carbon dioxide, a simple molecule in their environment, and water, another simple molecule in their environment, as starting materials to build a more complicated molecule, glucose. That's a sugar. And this is food for most living things on Earth. The chemistry also releases oxygen as a waste product. But this process of photosynthesis was hugely important in the story of life on Earth. And it was all powered by the energy from our sun. So because animals depend on plants for the base of the food chain, plants and animals alike, in fact most living things on Earth, are dependent upon our star, the sun. To end this lesson then, we'll consider the Goldilocks conditions as it applies to our Earth. Now, you may remember the story of Goldilocks and the three bears. At one point there are 3 bowls of porridge. One of them is too hot, one's too cold, one's just right. Well, we can sort of apply that principle to our Earth. There were several conditions that were just right for the Earth to be the kind of place where life might emerge. First, the sun was moderate in size, so it was a stable source of energy. Some stars are very big, some stars are variable stars. They change the amount of energy that they emit. The sun was a moderate star and a stable source of energy. The rocks and comets that made up the Earth had water in them, and that would form our oceans. And water is a critical substance. It's good at dissolving things. It would be the medium for lots of interesting chemistry that would happen on the Earth. The Earth's orbit was in the habitable zone and fairly circular, so no extreme temperature changes, and water can remain liquid throughout the year. So here's our Earth. It's in a fairly circular orbit. If it had a sort of an oblong orbit, it would be, way out here, it'd be real cold, and then it would get warm and then cold again. Well, liquid water might not be able to remain liquid at all points in the orbit if the orbit were oblong like that. So a fairly circular orbit keeps the Earth in the habitable zone all year. And there's a large sampling of different elements, again forged in stars, that allowed for a chemical diversity. So we want to think about the conditions on Earth were just right for lots of interesting chemistry to be going on. We've got lots of different elements that make up the Earth. Those elements can be dissolved in water, and the atoms can combine into molecules, and molecules can combine into more complex molecules. And in time, some 4 billion years ago, life emerged on our planet. Carbon-based life, dependent upon water, as we've seen before, and now adding, we're also dependent upon our sun. Our sun provides a constant source of energy that powers most of the ecosystems on our planet.